Okay, welcome to note set 15A, where we'll be talking about a concept called the null space, and this is covered in section 3.2 of your textbook. Nothing special about the A versus B for note set 15. Just when we originally made this note set for the on-campus version, we had it in one note set, and for the online version I felt it was more appropriate to split it into two, make the videos a little more manageable, and also I think conceptually it works better. So let's recall where we were at the end of note set 14. We were talking about this thing called the column space, which we denote with C of A. So A is some matrix, and we've abandoned restricting ourselves to just square matrices. We're now interested in, A can be anything, any kind of rectangular matrix, although the square one is still our main interest. There will be times when we have to deal with rectangular matrices in these settings. And so we've got one example here where we're showing what I refer to as a tall matrix. We've got 4 rows, 3 columns. Since there's 3 columns, we've got 3 variables. And since there's 4 rows, we've got 4 values in the B matrix, or B vector rather. And one of the important things that we saw in the last set of notes is that the only way that we have a solution for X is if the vector B lies in the column space of A. Because remember, this action of doing A times X is really forming linear combinations of the columns. So we'll have x1 times this column plus x2 times this column plus x3 times the last column. Those 3 vectors, weighted vectors, all add together to give us the B vector. So that's a linear combination. And since the column space holds all linear combinations, if B is not in the column space, there's no way to choose the x's to build the B vector. So that's a very important thing. Now we're going to get to the second most important aspect of this by asking the question, or remembering that the 0 vector is always in the column space of A. So that's partly because it's a column space, but remember, column space contains all linear combinations, so that includes 0 times the first, 0 times the second, 0 times the third, and adding them up, so you get 0. So 0 is in there. And so we could put all zeros here on the right-hand side. And it turns out that putting that there, even if that's not what we really want to solve, the action of solving for a general B leads us to ask about how do things work when the 0 vector is put over there on the right-hand side. So looking at this kind of problem where we've got some A times X, and I'm just illustrating it with this particular example, is equal to the 0 vector. If we can understand the solutions to that, and notice that I said solutions, we'll see how that all plays out in just a little bit. If we can understand the solution to that, it helps us understand the general solution or solutions to when we have a non-zero B here that might be of interest. So again, saying it, just restating it, even when we're not interested in the 0 vector on the right-hand side, we are forced to kind of think about that to understand the complete solution, and we'll see why in just a little bit. And so that concept is called the null space. So we're kind of giving it away that it is a space by its very name, but we'll actually prove later that the set of all x that solve this when you have 0 over here, that set is actually a vector space. So I will occasionally talk about things mapping into. So in this context, I might say all the x's that go in here, I'll do it with the general setting, all the x vectors that under the operation of A, map into the 0 vector. So that's just another way of saying all the solutions to AX equal to B. So the null space is all the vectors X that would map into the 0 vector under the operation of multiplying by A. So what's in the null space? So up at the top here, we're just restating what we just had on the previous slide, just so that we can keep it fresh in our mind and see it. But what's in here? What's in the null space? That's the important question that we need to ask. What is there? So certainly the 0 vector, right? Because if I take x1, x2, x3 all equal to 0, I'll have 0 times the first column, 0 times the second, 0 times the third, add them all up, and I get 0. So we know that that vector is in there, which is important because if it weren't, we wouldn't be calling it the null space. So we could have guessed that just from the terminology. Well, what else is in there? That's what we need to find out. And we'll see that for this particular matrix, that the null space is a line in R3. So notice that we're talking about R3. So that's because the X vector in this case is in three-dimensional space. That's because the A matrix is 4 by 3. So the B's, the column space is 4-dimensional. The null space will be in a three-dimensional space. And I should say that the column space is in a 4-dimensional space. It may have dimension less than 4, as we've seen that it could be a plane or a 3-dimensional hyperplane in 4-dimensional space. And in fact, we're seeing here that the null space is in R3, but it's not all of R3. It's a line, as we'll see in just a minute. So nailing down what is the shape, so to speak, of the null space within the full range that it could reside is an important question that we need to answer. And so for this problem, this particular A matrix, the vectors that will map to 0 all have this form. So these are the X vectors that will map into 0. So this structure is consistent across them all, and we can pick any value C, any scalar C, to give a vector that will make that will map into 0. So for this problem, you can see that if you take 1 times the first column, so 1 times this, take a 1 times the second column, take a -1 times the third column, those will all add up to 0. And then, any C is just going to pull out in front, so you'd end up with C times 0, which still would satisfy that. So we can see that this does satisfy it. It may be a little bit harder to see that it's the only form that satisfies it for this case, but it is true. And we'll see the tools in just a little bit that will allow us to establish that. And you can see here's our R3, and here's our 1 point. Remember, this comes from what we looked at previously as the special solution. And so we can see that it's 1, 1, and then if we extend this down, it's at -1. So there's that 1 point, and then we draw a line through that point in the origin. Because remember, we've alluded to the null space being a space, so it has to include the origin. So we'll just take all scalar multiples of this 1, 1, minus 1. So we've alluded to the fact that this is a null space, or I'm sorry, a vector space. But let's actually establish this. This, again, as I've said in the past, in a more theoretical math class, we would be proving lots of theorems, and that's not how this book works, and that's not how we're doing it in this course. We don't really care about developing your ability to prove theorems, we really want you to be able to think in terms of the concepts and use those to understand how engineering problems work. Notice I didn't say we want you to be able to solve for a specific answer. Yeah, we do, but the more important thing is that you can understand how things work, what makes it work the way that it works. So, is the null space a vector space? So we could also ask the question a different way. Are the solutions of AX equal to 0, do they always give some subspace of the space that the solutions could be in this case R3. So that's what we're looking for here. And we had rules that told us when something is a vector space. And mainly those rules are, closed under multiplication by scalars and closed under addition, or more equivalently, closed under linear combinations. So suppose we have two different vectors that are both in the null space. So here's V. It is in the null space because it maps to 0. Here's W. It's in the null space because it, under operation of A, maps to 0. So both V and W are in the null space. And then it's easy to see that their sum is also in the null space, because all we got to do is move A into here and into here, and we get AV, 0, plus AW, 0. 0 plus 0 gives us 0. So we know that it's closed under addition. Notice this was totally arbitrary, right? V and W are any two vectors that are in the null space, and then we showed that therefore it must also be true that their sum is in the null space. And then the second thing is multiplication. So V is in the null space, and if we take C times V for any scalar C, well, we know that we can pull the C out in front. So we have C times AV, but AV is equal to 0, and so that's equal to 0 itself. And so now we've established that multiplying by a scalar gives a vector that's still in the subspace. So what we've seen is that, yes, the null space is actually a subspace of the solution space. In this case, for this matrix, the solution space is R3, and we're claiming that the null space is this line. Now, we already knew that for this example, this line is a subspace. But notice that we just did this. It wasn't for this matrix. It wasn't for any special case. We did it in general. So that's kind of the power of being able to at least do informal proofs like this, that you can establish that, hey, this is not true. This is not just true for this example. It's true in general. And that's an important thing to be able to establish. So let's look at this. We've got these two spaces that we're playing around with here. We've got an m by n matrix. We've got an n by 1 vector. Notice that the n's are matching up so that they can multiply. And we're seeing that our solution vectors x have n components. So they're vectors in Rn, and the null space will be some subspace of Rn. So you need to get to the point where you can look at a matrix and you can say, oh, all right, I know that this number here is going to tell me the space where the null space will be embedded. And then the other one is we've got columns of A. Each column has m components. So it's important to recognize that we're not talking about n here. We have n columns, but each column has m elements. So the column space is going to be a subspace embedded in Rm. So we've got those two subspaces, the column space and the null space. And so here's one way I like to look at it. This picture is not out of the textbook. This is something out of my head. So let me explain it just a little bit here. But I do want to point out that I tend to use ellipses and blobs to illustrate high-dimensional vector spaces, even though we can't really draw them. So I need you to realize that I'm not saying Rn looks like this ellipse, and I'm not saying that the null space looks like this dashed kidney bean shaped thing here. I'm not saying that. So these are, evocative of the spaces, but not precise characterization of what the spaces actually look like. So make sure that you realize that I'm not literally showing you shapes of things here. But we've got some space Rn, so that's the space where the x's live, right? So solution vector x has n components. So we can pick any x over here and quote-unquote map it with the matrix A over into some vector in Rm. And the question is, what vectors could we end up with? So we're kind of flipping the perspective around a little bit. We've been saying we're given A, we're given B, what X solves it. But for the moment, let's ask the question the other way around. We're given A, and now we're free to pick any X in Rn. What B vectors can I get from doing that? Well, we know that we can only get to vectors that are in the column space of A. So this little dashed thing here, it's not really kidney shaped, I don't know what it's shaped like, but that little dashed region, that's what I'm saying, again, evocatively, is the column space of A. So no matter what I pick over here, I can pick another X, it will map to something inside there. I can pick another X down here, it might map to something over here. But I can never get something out here, okay? Never. Now, so that's showing the column space embedded in the target space, Rm. So anything in the originating space or source space, I can pick anything there, but I can only hit things in this target space that are in the column space of A. Now, what happens if I pick this vector? Well, I'm claiming that that will map to 0, which is in the column space. And so here's another vector that if I map that with A, will map to 0. And yet another one that will map over into 0. And in fact, I'm trying to illustrate, again, with evocative pictures, not precise characterizations. This little kidney bean shaped area I'm calling the null space. So anything in that little kidney bean will map to 0. So here is another point that will map to 0. And so these are good ways to visualize what's going on in these. So it's important to remember that the null space is embedded in the space that the X comes from. The column space is embedded in the space where the B comes from. And even though we may be interested in solving AX equal to B where A and B are known, it's often useful to think about picking, for the given A that we've got, think about picking an X and seeing where it ends up. And so that's kind of what we're thinking about here. And it helps us understand this. So keep this picture in mind as we go through this. So the null space is a space. Well, it's a subspace, and so therefore it's a space just on its own. So what about if we were to look at the case when B is not equal to 0 and ask about the set of solutions? Is that a space? So would that be a subspace? So if the right side B is not 0, for example, using this matrix that we've been using to illustrate things, suppose we put 1, 2, 3, 4 over there as our B. Well, first question is there a solution? Well, there is for this case, because clearly our B is in the column space because it actually equals the first column. So obviously, one of the solutions to this is the x vector 1, 0, 0. And so we now ask the question, does this by itself and other things that can be formed from it, does that even form a subspace? And I'll give you a hint. There is an easy way to check this. It does not require too much work to do this. Why don't you pause the video here, give a little bit of thought to that. Don't look ahead on the next slide. Give a little thought to this, come back armed with your answer, and hear what I have to say about it. All right, so pause the video. Okay, so hopefully you paused the video and gave it a shot. Really, these are that's the best way to try to learn these things, is to just give an attempt. Whether you're right or wrong matters less than if you gave it an honest try. So one easy way to check this is, so suppose this is a solution. Well, it is a solution. So we need to have C times that must also be a solution in order for the set of solutions to be a subspace. So if we put in A times CX, well, we can pull the C out in front. That's going to give us C times AX. And we already know that AX is equal to B. So this gives us C times the B vector. So let me put a little couple. We've got double line under that. We've got single line under that. Double line to show that's a matrix. Single line, single line. So clearly this is not a solution because it doesn't map to B. It maps to C times B. So we already know that the answer to this question is no. So the set of solutions to a non-zero B does not form a subspace. So that's kind of an important concept here. And we can look at this here another way. So if the right side of B is not zero, the solutions of AX equal to B do not form a subspace. But there are several solutions. So here's one. Here's another one. You can verify that that actually works, right? So we would be subtracting 1 from 2 gives us 1. Subtract 1 from 3 gives us 2. 1 from 4 gives us 3. 1 from 5 gives us 4. So yes, this is a solution. But those will not form a subspace. Another way to verify is that the subspace, in order for this set of solutions to form a subspace, it must hold the zero vector. But if we put the zero vector in as our solution, we don't get 1, 2, 3, 4. We get 0, 0, 0, 0. So that's the second easy way to verify that there's no way that the set of solutions can form a vector space. Only when B is equal to 0 does that work. Now, these are not two separate things. They, as we'll see soon, thinking about it for the case where the B vector is equal to 0 is an important part of solving it for any non-zero B, as we'll see. So, the fact is that we have not only just these two solutions, but we've got many solutions. In fact, there will be infinitely many solutions, as we'll see, for this matrix. Some matrices, as we know, will give unique solutions. So, in particular, when A is square and invertible, we've seen that. So we've got a lot of solutions here, but they don't form a subspace. So we saw on the previous slide, one reason was that scalar multiples times a solution does not give you a solution. And now we've seen here that the zero vector is not included, so that can't be a subspace. And so here's an important question that will be something that you need to answer when you're solving real-world problems. So, why do we have multiple solutions for this case? So another way to ask this question is, when do we have multiple solutions? What are the conditions that lead to multiple solutions? We already know the conditions for when there is no solution. That's when B does not lie in the column space of A. But all right, suppose we pick a B that does lie in the column space. Are there times when we'll have unique solution? There's just one solution to it. That's a good scenario in the engineering world. This is the answer to the problem. But sometimes, as we see here for this matrix, we have multiple solutions. We're showing 2 above, but there's actually infinitely many of them. Why do we have that? Well, one initial insight into this is that, as I just said, we already know that when A is square and invertible, we had one unique solution to the problem. AX equal to B, you invert A, you multiply A inverse from the left on both sides, and you get X is equal to A inverse B. One and only one solution, and everything's good. But in this problem, we're seeing that A is not square. So you might think, anytime A is not square, we'll have multiple solutions. But actually, that's not true either. So we need to dig deeper into this and try to understand what is it that gives rise to the case where we have multiple solutions. So that if we're trying to design something where we know there will be one and only one answer to it, we'll know what conditions we need to impose on our system that leads to the A matrix so that that can't happen. And that's why we as engineers care about this stuff. So the first step towards this is to understand what are the forms. What's the form for the solutions? We've got AX equal to B. How do I find the general solution to this thing when there is a solution? So let's consider the case where B is in the column space of A. And so how does this work? So first of all, our first insight to this shows us why this null space is important to us. So suppose we've found some solution X. We've got a solution X. We know that it solves AX equal to B. All right, good. We've got one solution. Are there other solutions? Well, let's say that we know that Z is a solution to AX equals to 0. So we know that Z is in the null space of A. And now watch. We can take the one solution that we know, put it there. We can take the one thing that we know is in the null space. There may be others, but we don't know yet. We just at this point know that Z is in the null space. And we multiply it by any number C. And my claim is that this vector is also a solution. I say solves AX equal to B. It's a little bit of a misnomer. What I'm saying is all of this gets replaced into there. And let's see how that works. So is this a solution? Well, to check it, put it in and see if we get B out. So we put in X plus CZ. We can now pass the A through, and we can pull the C out in front of that as well. So we get A times X, and we get C times AZ. But hey, AX, we know X was a solution, so that gives us B. And AZ gave us 0, so C times 0 is 0, and B plus 0 is B. So look at that. X was a solution that by itself maps to B, but so is X plus CZ for any value of C. So as soon as I have one thing in the null space, I know that there are infinitely many solutions to this problem. And it's important that you see the role that the null space plays in this. It's the null space that gives rise to the multiple solutions. So we've pretty much answered our question on the surface anyway. If the null space only contains the 0 vector, if that's the only thing in the null space, then there will be a unique solution if there is a solution. So if B is in the column space and A has a null space that is only the 0 vector, nothing else, then there will be one and only one unique solution to AX equal to B. And so that's kind of neat. So this null space we're seeing here plays a very key role. So to answer the question, when do we have a unique solution, we need to focus on characterizing the null space of A. We need to find out for a given A, what is this null space? What does it look like? How many vectors are there in it? Is there only the 0 vector in it? If there is, we know that we'll have a unique solution. If there's more than just the 0 vector in the null space, then we know that there will be infinitely many solutions. So this is our key, literally, to opening that lock. So it'd be nice to have some sort of way, some sort of algorithm to find what the null space is. And in fact, we can do that. And we'll actually see that there is a nice little piece of MATLAB code that will calculate what the null space looks like. And it's based upon the ideas that we'll lay out here. And the last slide in this set of notes will talk a little bit about that MATLAB function. So how can we solve using some sort of algorithm the AX equal to 0? So let's look at an example. This book loves to build up to things with examples rather than just throwing out theorem, 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 and theorem proof, theorem proof, theorem proof. And that's kind of why I like this, because this is really kind of how engineers and mathematicians, for that matter, discover things. It's you play around, you look at some examples, you try to find what will work, what doesn't work, and then you try to extract from that what are the general principles that you need. So that's kind of how research works. Well, this matrix is singular. So you remember, singular matrix means that the columns for a square matrix is when we're talking about singular or non-singular. Square matrix, we say it's singular when its columns are linearly dependent, and we can easily see this. We just see that the second column is 2 times the first column. But let's take a look at this case where the matrix is singular and apply elimination to these equations to solve for the x that give us 0. So there's rewriting the matrix form AX equal to 0 in terms of 2 equations and 2 unknowns, which would be the case for a 2x2 matrix A. And after we do elimination, I don't show the steps here, but by now you should be able to do elimination. We quickly result in a new system, equivalent system of equations where we really only have one equation that matters. The second one, 0 equal to 0, always satisfied. So really there's just one equation, so we can kind of cross that one off. So there's one equation in 2 unknowns, and if we look at this, we've got x plus 2x2, x1 plus 2x2 is equal to 0. That's actually a line. So if we think about solving that, we've got, we can rewrite it this way. x1 is equal to negative 2 times x2. So that is a line. If we think about this as y is equal to mx plus b, so there's our x, here's our m, and we have no b, so it's plus 0. So remember, the b is the intercept. So this is a line with slope of negative 2. Well, in terms of x1. If we were to do it in terms of x2, we would have a slope of negative 1/2. So we would have x2 is equal to negative 1/2 x1. So it's a line. It's a line in, well, I say here Rn, but really this is in R2. So it's a line in R2. And this line is the null space. So, you should be able to, and I'll leave this to you as a little exercise, you should be able to take x1 take a set of axes x1 and x2 and draw what this line looks like on that set of axes. So it goes through the origin. So any point on that line is the tip of a vector that is in the null space. So from that we can say that the null space will contain vectors with elements x1 and x2, where x1 is constrained to be equal to negative 2x2. So look at this. We're not able to freely choose both of those. Once we choose one of them, the other one is nailed down. So if you choose x2, x1 will be negative 2 times whatever you chose for x2. And so this is the null space. So it contains all solutions. Now here the solutions are ax equal to 0. So it contains all solutions for ax equal to 0. And so just to motivate what we're going to be doing in just a little bit, there's an efficient way to describe this line of solutions. So we basically choose one point on the line, and we're going to call that the special solution or the special vector solution. And then all points on the line are just multiples of that one point. And this works because we're talking about a line that goes through the origin. That's why we can define a single point and then get all the other points on the line by just multiplying that one thing by a scalar. It wouldn't work to describe a line that doesn't go through the origin that way. So for instance, if we just pick x2 is equal to 1, then we can solve, we let x2 equal to 1, so we'll end up with, so we can cross it off since we let x2 be equal to 1. We have x1 plus 2 is equal to 0, tells us that x1 must be minus 2. So our special solution vector, which we'll call S, is this. And remember, that's really showing a column vector with minus 2 at the top and 1 underneath that. So the null space of this given matrix, here's our special vector, and it'll be all multiples of that. So we would just put a C in front of that, will give us the entire space. So that was the case where the null space was defined by a line and could be described in terms of a single vector because the null space had one dimension, right? A line is a one-dimensional subspace, and we need just one vector to span it. So our one special solution vector spanned the null space. But in general, we'll have a higher dimensional null space. So it could be 2, 3, 4, whatever. How high it can go will depend on the space that X can be in. So remember we talked about that. We said that X, if we back up here, we said that X is in Rn. So we're looking for a subspace of Rn. So for an m by n matrix, the highest dimension we could have for the null space would be n, but we're more likely to have things that are lower dimension than that. In general, that the lower the dimension, kind of the more desirable in some sense, because remember when we have dimension 0, that means that there's only the 0 vector in the null space, and that's when we have a unique solution. So in general, there will be multiple special solutions. In fact, there will be one special solution for each dimension of the null space. And then the null space will be the span of these multiple special solutions. So remember, by span, we mean all linear combinations of the special solutions. So that's where we're headed. So let's look at some examples here. So let's describe the null spaces of these three different matrices, A, B, and C, where B is defined in terms of A, and C is also defined in terms of A. So we've got this square A. Is that the one we just looked at? 1326? No, not quite. It's 1328, so it's a little bit different. So let's go through this. Now, if we look at this, remember we had 1326, and we showed that this column was a multiple of 2 times the first column. But now we have 28, so clearly it's no longer a multiple. So that means these two columns viewed as two vectors in R2 don't lie on the same line. So that means they are linearly independent. That means that A is non-singular, A is invertible. We know that that's the case where we have a unique solution. We've already alluded to the fact that we get a unique solution when the null space has only the 0 vector in it. So we could puzzle all this out already based upon things that we've stated or at least alluded to. But we can also see this from applying our steps of elimination. So if we do elimination on this, we start here. So here's our starting system, and then after elimination we get to something that looks like this, and from that we can see, okay, so we've got an upper triangular matrix here. So there's our first solution is x2 is equal to 0. Now do back substitution. So we let x2 be equal to 0 for this top one. So we're going to have 1 times x1 is equal to 0, which gives us that x1 is also 0. So there's our 0 vector. And that's the only one that there will be. That's the only solution because of the structure of A. We know that it's non-singular or invertible. So A is invertible, so there are no special solutions, well, other than 0, but that's really where we say there's no non-zero special solutions. So all columns of this A have pivots, right? Here's the pivot for that column, here's the pivot for that column. So that's the other characteristic that we can check. If your A has a pivot in every column, then you know that that you're good. That the only solution that you'll have is the 0 solution. All right, let's continue on. So we're now going to look at B, where we take A and stack A on top of 2 times A. So now we've got a tall rectangular matrix, and the claim is that this has the same null space as Z. So it's pretty easy to see that when we put the x1 and x2 here, this top part has to still work with those to make 0. So those will still have to be 0 and 0. And putting this down here doesn't really allow any other solutions because those have to be 0, 0 to make it 0 at the top. So putting the thing at the bottom doesn't add any additional generality that allows us to get other solutions. They just impose further conditions on X, and so they can't loosen up the conditions. So this matrix B also has 0 null space. And if you went through and did elimination on this, you would still find that every column has a pivot, and so therefore we can solve this only for the case of x equal to 0. Now let's look at C, which has A and 2A stacked side by side. So we end up getting something that looks like this. Where'd my pointer go? There it is. So we've got A and 2A. So remember, we knew that these two vectors are linearly independent, but obviously these two are just multiples of each other, so they are dependent. And these two are multiples of each other, so they are dependent. So really we only have 2 linearly independent columns And that's a key insight here. So we've got extra columns, and because these are linearly independent, or linearly dependent rather, sorry. The last two depend on the first two. And so these last two columns are what we'll call free columns. And we'll explore this idea further, but let's do our elimination on this. So we end up getting a pivot here and a pivot here. So we end up with just two pivots. We've got four columns. So the last two columns don't have pivots, and so those are our free columns. So soon we'll be talking about doing this kind of elimination, or something even a little bit further than this, and looking for the pivots, and then looking to see what else is left. And the things that are left will be called the free columns. And obviously the things that have pivots in them will be called the pivot columns. And so this will tell us something about the null space. And what we'll see will be interesting as we go through this. So this is just reiterating this. If you go back and look, here's the U matrix that we just had. So here's the U matrix. So the columns with pivots define the so-called pivot variables, and the others define the free variables. So remember, we're going to be multiplying this by, x1 all the way down to x4, because we have a 2 by 4 matrix, so our solution space lies inside R4 in this case. So when we're talking about the pivot variables, since these are the pivot columns, x1 and x2 will be the pivot variables because they correspond, they will multiply times the pivot columns. And then in this case, x3 and x4 will be the so-called free variables. So you do the elimination, find where the pivots are. Those columns positions will define the positions of the pivot variables. You find the rest of the columns, those are the free columns. The positions of the free columns will define the positions of the free variables. So that's how we do all that. So in this case, x1 and x2 are the pivot variables, x3 and x4 are the free variables. Now here they're separated. Pivot variables are at the top, free variables are at the bottom. It won't always be that way, as we'll see. So these could be, interwoven in some way. So here's the deal. The free variables are called that because once we pick those, we can pick those on our own. And then, as we saw in a previous slide just a few minutes ago, there will be constraints as to what the pivot variables need to be. And so the total number of special solutions that we'll have will be equal to the number of free variables, or equivalently equal to the number of free columns, which we can figure out is the total number of columns minus the number of pivot columns. So we'll nail that down in an equation form later on, but I think you can see that here, that you start with the number of columns. So we've got an m by n, so we've got n columns. In this case, 2 of them are pivot columns, so we'll take n, in this case 4, minus the number of pivot columns. 2 gives us 2 is the number of free columns or free variables. And that's the number of special solutions that we'll have. So we already know from this that the number of free columns that we have will end up giving us the dimension of the null space, because we've already said that the span of the special solutions will be the null space. Now, the only thing we haven't really established is whether these special solutions will be linearly independent, and they will. We won't prove that, but it'll be pretty obvious. So for our case, we can easily find these special solutions by just simply setting our free variables appropriately. So we're saying up here that we very cleverly pick some combination of 1s and 0s to make these special solutions. So basically, we're saying, consider the case where one of the free variables is 1 and all of the other free variables are 0. Then we would cycle our way through that. So in this case, here we're saying x3 is 1 and x4 is 0. And if you plug those into this system using the U matrix, you can easily solve for what x1 and x2 have to be for that case. Now you flip it around, set x0 equal to 1, x3 equal to 0, x4 equal to 1. Solve that system and you'll get 0 and -2. Those are our solutions for the pivot variables for our special solutions. So as we said, for this case, we've got 2 free columns, so we'll have 2 special solutions, and there they are. So it was pretty easy to find them this way. So just reiterating our definition or characterization of what's pivot and what's free. And so since the free variables really can be anything, we've just used these 1 zeros to nail down one point. So hey, look back at that slide where we had that line that described the null space, and we said, pick one point. I think it was 1, 1, -1. That was our special solution, and then all the other vectors in the null space were some multiple of that. Well, that's what we're doing here. We're picking one special solution, and we're just cycling through the free variables with the 1s and 0s, with just a single 1 allowable at any one time. It's a little hard to see that in this case since there's only 2 free variables. Then once we have those, instead of in that case where we had one of them, where we just looked at a scalar multiple, well, when we have more than one of them, we have to look at a linear combination of them. So in our case, we've got 2 of them. So here's S1, that's one special solution. We've got S2, that's the other one. And the things that we scale them with are the variable symbols for the free variables. And you can see what ends up happening here, right? When we set x3 equal to 1, then we multiply by x3 out in front. What we're really doing is allowing this free variable to run over all possible values while keeping the other free variables set to 0. And we see what happens with the pivot variables. And what we'll see is that for this case, x2 will always be 0, but x1 will be -2 times x3. That's the constraint between the free variables and the pivot variables. And likewise, we would weight the other one by x4. And so if we just multiply this through, add them all together, so we multiply our x3 through and we get this, we multiply our x4 through and we get this, we now add all those together, and we get this as the form for our solution. So that's the complete solution to this matrix equation. C, which remember we formed for this example from A and 2A. So for that matrix C, the complete solution for the null space looks like this. So this is, remember, 2-dimensional, we said. We had 2 special solutions. Those span the null space. This is the complete solution for the null space. So this defines some plane in 4-dimensional space. And that's pretty cool. So just another comment here. In this case, we did elimination up to this point, so we could identify what the pivots were and then see where our free columns were. But we'll find it better to actually go further into what's called reduced row echelon form. And so for this problem, it ends up looking like this. So notice that what we've done is we've eliminated everything above and below the pivots. So we got rid of this, we turned that into a 0, and then we normalized by this to give us this. So we've done this already when we did the Gauss-Jordan elimination. It's along those lines. It's basically the same ideas. And this is called reduced row echelon form. And so when you do reduced row echelon form, this is what you get. So all your pivots are 1s. There's zeros below, which we had over here in the regular reduced form, but also above. So we get them up here as well. And the pivot rows and columns form an I matrix. So in this case, it's very easy to see the identity matrix there. But we'll see in the next example that the pivot rows might, well, the pivot columns might be interwoven with the free columns. So you won't see that identity matrix structure sitting there all grouped together. So it'll be easiest to see that in an example, which we'll see in just a little bit. And so from this, this is how the reason we go to this structure is that all these ones and zeros makes it really easy to solve. So here's the steps that we went through before, setting x equal to 1 and x4 equal to 0. So that's one of our special solution setups. And we saw that we got this structure. And setting them the other way and solving gives us this structure, or that solution. And then we saw that we could combine those to get our final solution. So that's what we just did. And I'm just pointing this out to show how this usefulness of this reduced row echelon form is for solving these equations. But it's actually even better than that, because we can do all of this by inspection of R. We don't have to actually write out equations and even solve them. So here's the R that we just had, and there's everything we just went through on the previous slide, which was characterizing everything we went through on slides before that. So this is just systematically showing how we use these special selections to get our special solutions. But let's see how this really works. So notice that we've got our two special solutions are set by how we pick x3 and x4. So if there's more than just two elements, we will never have more than just one of them be 1. So one of them will be 1, all the others will be 0. That's kind of key. But in this case, what do we do with them? So for the first pattern, it just comes right down here as a column. And the reason that we put it down there is that, well, that's the position of the free variables. So we're really going to put those wherever, in whichever position are indicated as the free variables. We don't always put it at the bottom. We'll see in the next example a case where everything's interwoven. The other solution, 0, 1, we see comes down here. And so we'll see basically an identity matrix occurring down here. And what goes in the top? Well, we solved the equations, but because of the clever choice of ones and zeros, it gets rid of most of the machinery that comes to play in the equations. And so the only stuff that really plays are these numbers here. So the way this works then by inspection is that we just go, okay, you see this minus 2, 0 that we got for our solution? That's actually this free column. And you see this 0 minus 2? That's actually this free column. Well, almost. Notice that there's a negative sign. So what we really need are the negative columns of R for the respective free variable. So so the one where x3 is equal to 1, we go to the third one that corresponds to x3. We take that column and we negate it and we put it up in the top. In the top for this example. We'll see in the next example how we have to interweave them. For the x4, that's the one that's set to 1. That's why we have the x4 out in front. We go to the fourth column, extract it, multiply by negative 1, or just another way to say that, negate it, and we're good. So in some cases, we may have extra rows down here, and so we don't take everything. We need to end up with the right number of variables in here. There needs to be 4 of them. So we may end up with too many things if we took the entire column. So what we need to do is start from the top and take the number of elements that equals the number of free variables. In this case, we don't have that extra row, but we'll see in a subsequent example how that works. So here's an example that shows some of the deviations from that simple case. So our pivots now, here's our R matrix. So this is after the reduced row echelon form has been computed. And we can see our pivots. So here's one pivot, here's the other pivot. I already have them nicely indicated there. And you'll notice a couple things. That means this is a free column, that is a free column, and you can see that they are interwoven. So to see that identity matrix that comes from the pivot columns, you need to look at extracting those parts. And you'll also notice that there's an extra row at the bottom, so we don't extract that to see that identity matrix either. So you kind of have to know where to look. And it's hard to write down the rules, so it's easiest to just illustrate. I think between the previous example and this example, you can kind of see how it works in general. So we've got two free variables because we have two free columns. We had two pivot columns in this case. All the remaining ones are free variables. So we're going to have two special solutions. And we've already seen that these can be extracted by inspection from R, the reduced row echelon matrix. So here's how we do that. Remember I said start from the top and take number of elements equal to the number of free variables. So our S1 will correspond to X2. So we go to 2, the second column. We've got two free variables, so we're going to take the top two elements, and then we need to interweave them. So we interweave them into the correct positions where the pivot variables are. So the pivot variables are in position 1 and 3, so we put those in 1 and 3. And then the other things, 1 and 0, for our special structure, they actually go where the free variables go. So that's the structure. So there's S1. That's our first. We know that there's one more. That also tells us that the dimension of our space is going to be, of our null space will be two-dimensional. And then we put, for the second one, we go to X4 is equal to 1 in that case. So we go to the fourth column. There's two free variables, so we take the top two elements and we put them in the positions. And we have to negate them. I didn't mention that. We negate them and we put them in the positions of the pivots. Then we pick this structure and put it in the other positions. And remember, this structure is always going to be a single one with all the other free variables set to 0. So that's exactly what we would have for this case. So hopefully that makes sense. I would encourage you to play around with this example, try it, following what's shown here, then put everything away, try it on your own, try a few other ones. You can always check to see if you got the right answer by multiplying in MATLAB R times what you think is one of your special vectors. If it comes out to be 0, or at least some really, really small number, then you've found one of the special vectors. So let's summarize some things here as we draw this lecture to a close. It's been a long one, but we had a lot to say. So this is a key idea called the null space. We saw that it is a space, and how do we find it? Well, the pivots set location and number of pivot variables. All the other variables are called free variables, and we saw that the easiest way to identify these things are through the reduced row echelon form. And then for every free variable that we've found, there will be a special vector. We didn't talk about why these things are definitely linearly independent, but it comes from putting in those zeros and ones for the free variables ensure that these special vectors will actually be linearly dependent from each other. So we'll put in, we'll find as many special vectors as there are free variables. So that will tell us the dimension of the null space. And then we form a linear combination of the special vectors. And remember, the weights that we put on that linear combination are the symbols for the free variables. So in a sense, what we've established here is that once we find those special vectors, the null space is just the span of those special vectors. And since the special vectors are linearly independent, the dimension of the null space is the number of special vectors. So one last comment. So we alluded to this earlier. For some matrices, the only solution to AX equal to 0 is the 0 vector, which means that for those, the null space contains only the 0 vector. And we said, aha, that's precisely the case where the solution is unique. So the solution to a general AX equal to B, where B is in the column space of A. So another way of saying that is, and we'll talk about this more later, so when we have a 0 null space, that tells us that the columns of A are independent. So there's an easy way to check to see if you've got independent columns in a matrix. And if you're just given a bunch of vectors and you want to know, are these linearly independent, you can just stick them into a matrix and then go through this process to find the null space. And if your null space ends up being the 0 space, you've just computationally showed that those vectors are linearly independent. So that's really nice. And our last slide here is a M file, a MATLAB function. So this would be you put this in a, we'll talk more about this later, but you store this, and it looks like here they've made an error, so that actually is the correct address, but I had to do a little tidying of it. I wanted it to be NULL, so I changed that here, and I changed it in the name of the file as well. So if you don't do that, it won't work exactly like I showed here. But basically, you store this file. So it's a .m file, and we'll talk more about this. Store that in your directory that MATLAB is pointing at, and then you can use it. And so you take your matrix A, and you would literally, so here's an example of calling it. I create the matrix A, and I call n is equal to null basis A, and it will give me back a matrix n that will contain the special solutions. And so then you can check to see that it is. But let's take a look at what's going on in here. So apparently there's a command called RREF. Ha, I bet you can guess what that is. Reduced row echelon form. And we'll talk about that more in a subsequent set of notes. So this is a common thing to do early in an M file and MATLAB program, is to, if you've just started working with a matrix A, you'd kind of like to know what its sizes are, you know, how many rows, how many columns. And this thing, this variable from RREF will give you pointers, the indices of the columns of A that are the pivots. So that's pretty obvious from the name, pivcol. So the length of that will tell you how many pivot columns you have. Now we want to get a pointer into the free columns. So pivcol will allow us to extract the pivot columns. Now we initially create free col is equal to 1 to n, and then we just talked about this in a MATLAB lecture, assigning empty vectors. So here we are assigning an empty vector to free col, which is now just a row vector, and we're assigning an empty vector to every place where there was a pivot column. And so that's eliminating the pointers to where the pivot column is and leaving the numbers that are 1 through n that point to the free columns. So at this point, free col contains the indices into the free columns, and pivcol contains indices to the pivot columns. So that's beautiful. Then we just set up a big zero matrix, and we shove in the things that we need. So what did we shove in? Well, we need to shove in essentially an identity matrix everywhere there was free columns. So that's just shoving in that structure of everything is zero except for one free variable. And then in the remaining positions, and you can see that we're putting those in where the free column locations are. Then we're going to extract from the R matrix. So this is the R matrix, which is the reduced row echelon form. We take the first R rows of it, so that was our start from the top and go down as many locations as pivots. So remember, R here was the number of pivot columns. So we're going to grab the first R rows, and which columns do we grab? Those that we said were the free columns. So that's exactly what we did. So the ones that are in the free column position here go into the pivot column positions of N. And then we're done. And so that's pretty cool. So I would encourage you to kind of work your way through this. You can type this in at the command line just as it is, just one line after another. And you should be able to do it for a simple example and see, look at the results for R, look at the results for free call, look at the results for pivcol, and see what they are. And explore. That is really the only way, the best way to learn how to do all this stuff. So that's the end of this lecture, and I'll see you in the next one.